Okay, reaction profile diagrams. How to interpret them. So, we're asked how many elementary steps there are and what the rate limiting step is. Remember, each hill represents an elementary step. So, there are 3 elementary steps. And the slowest one is going to be the rate determining one, and that's going to be the one with the greatest activation energy. And we can see here clearly that this step, the second step, has the highest hill to overcome in terms of energy. So the rate determining step is going to be number 2. So 3 steps with the second step being the rate determining step. In which of these would Kc equal Kp? So the relationship between Kc and Kp is Kp, the equilibrium constant with respect to partial pressures, is equal to Kc times R, the gas constant, T, the temperature, to the delta N. And remember, delta N is equal to the moles of gas and the products minus the moles of gas in the reactants. So, in order for Kp to equal Kc, we need delta N to equal 0. Because if that equals 0, that means RT to the 0th will be equal to 1, which will cancel out this entire thing and have Kp equal Kc. So, we're looking for an equal number of moles of gas in the products and reactants. And if we look at choice A, we have 2 moles of gas in the reactants and 2 moles of gas in the products. So it turns out, actually, our quest here is done. The answer is choice A. We're trying to find here which of these reactions has an entropy change greater than 0. So with entropy, there's 2 real ways that we can create a noticeable entropy change in a reaction. So remember that in terms of absolute entropy, gases are greater than liquids, which are greater than solids. And for our purposes, we can treat aqueous things somewhere in between gases and liquids. The other way that we can increase entropy is if we have more moles of gas in the products, or more moles of products than reactants in a given phase, that leads to an increase in entropy. So if we go through choice A, we go from 3 moles of gas to 2 moles of gas. No, that's going to be a decrease, so we can get rid of this answer. In choice B, we go from 2 moles of gas to 1 mole of gas. Again, that's a decrease. In choice C, we go from 2 moles of aqueous to 1 mole of solid. No, again, that's going to be a decrease. In choice D, we go from 1 mole of solid and 1 mole of liquid to 3 moles of aqueous. And that's going to be the increase because aqueous, generally speaking, has a greater absolute entropy than its liquid and solid counterparts. And then finally, in the last choice, we're going from 2 moles of liquid and 1 mole of gas to 2 moles of solid. Now, forget about it. That's going to be a decrease. So the answer is D. Which of these is likely to act as a Lewis base? And a Lewis base is an electron pair donor. So we need something with an electron pair that's readily able to donate itself. And that's going to be, we can't see it in our structure here, but choice E, actually, the way this is drawn, would have 2 lone pairs of electrons. We have a nitrogen with just 2 bonds to it. Should actually have a negative formal charge. But regardless, this nitrogen here on this amine is going to have a lone pair of electrons that it can donate, so choice E for the win. In this problem, first we need to determine what order this reaction is. So an ester enthusiast is creating an ester, in this case a rum-scented ester. Cool. And we have this reaction here, and we're given some data. And if we look at our data, in plotting natural log versus time, we get this data that it's more of a curve. It's not a linear trend. So this tells us that we're not looking at a first order reaction. However, if we look at 1 divided by concentration versus time, look at how these data align with each other. This is a linear trend. This tells us definitively that we are looking at a second order reaction. The other thing that we can glean from this is, if we look at, we're trying to find the rate constant. So remember that if we plot 1 divided by concentration versus time and we get a linear trend, our slope is going to be equal to our rate constant K, which means that the rate constant K is just going to be equal to 0.0111 molarity to the -1, S to the -1. So the answer is E. In this problem, we're trying to figure out what will happen if we add sodium chlorite to a solution of chlorous acid. So what I like to do whenever there's a question that says, what happens if you add this to that? Think about what's going on with our original solution. So chlorous acid, HClO2, is a weak acid. It's going to dissociate into H plus and ClO2 minus chlorite. Okay. So now, if we're adding in sodium chlorite, so sodium chlorite, any sodium salt is going to associate completely into sodium, and in this case, this is going to be chlorite, ClO2 minus. So the Na plus is just going to be a spectator ion here. What we're interested in is the ClO2 minus. So if we add in this salt, again, it's just a source of chlorite, it's going to increase the concentration of products. Le Chatelier's principle tells us that this will cause the reaction to shift to the left, which will have 2 downstream consequences. First of all, it'll decrease the concentration of H+, and it will increase the concentration of HClO2. So, which of these will happen? The H+ concentration would increase. No, I think not. That's not true. It's going to go down. The pH would increase. Okay, so what does this mean? pH would increase means the solution is becoming more basic. And if we think about this, there's 2 ways of thinking about it. First of all, the H+ is going down, which means it's becoming less acidic, which means it's becoming more basic. The other way that we can think about this is ClO2 minus. What is that identified as? Well, it is a weak base, which means the pH would indeed increase. This would get more basic. Choice 3 says the HClO2 would increase, and we can see here that is indeed the case. So we're going to count this, and it says the OH minus concentration would increase. So if the solution is becoming more basic, which we've established it is, that means, by definition, that we must be getting an increase in hydroxide in our aqueous solution. So 4 is also indeed true. So 2, 3, and 4 are all true. Here we're trying to relate a voltaic cell to the amount of work it can perform. And remember, we have standard cell notation here, which gives us on the left-hand side the anode. So we're oxidizing chromium. And on the right-hand side of this double bar here, we have the cathode compartment. So we're reducing silver. And in both cases, the nitrate is just acting as a counterbalancing ion. So the nitrate here is just acting to counterbalance the chromium 3+. And likewise, this nitrate is just acting to counterbalance the silver plus. So, when we write our reactions, first let's write out the reduction of silver. So, silver plus an electron to yield solid silver has an E standard 1/2 of positive 0.799 volts. Okay? So then the oxidation of chromium. Chromium going to chromium 3 plus, and 3 electrons, that has an oxidation potential of 0.763 volts. Remember, we have to flip the reaction on our reduction potentials table, and we have to flip the sign on our reaction. So, total, this gives us an E cell of 1.562 volts. And remember, that's what we get from adding together the reduction potential of what's being reduced plus the oxidation potential of what's being oxidized. Now, the question specifically asks, though, for the work that this can do. So we need to use the equation, delta G. So whenever we think of work, we think of delta G, the free energy, is equal to negative N times F times the, in this case, we're looking for delta G standard, so the E cell standard. Now then, what is N? So N represents the moles of electrons transferred in the balanced overall reaction. And if we look at the reaction up here, we have 3 electrons in the oxidation, which means we would need to have 3 electrons in the reduction. So we'll multiply all these by 3, which means N is going to be equal to 3. F, Faraday's constant, well, that's a constant. That is equal to 96,485 coulombs per mole of electrons. And then our E standard is equal to 1.562 volts. So all of this collectively is equal to our delta G standard. When we multiply all this together, moles of electrons cancels out, and we get Coulomb volts. And remember, Coulomb volts is just a fancy way of saying joules. So this ends up equaling negative 452,000 Coulomb volts, which again just means joules. So this is equal to roughly 450,000 kilojoules worth of work. The negative sign just means that this is free energy being released. So the magnitude of work that it can do is about 450 kilojoules per mole worth of work. What is the pOH of a 0.15 molar solution of hypochlorous acid HClO? So how would we identify HClO? Well, it has a Ka, which means it's an acid. It's also not one of our strong acids, so it's a weak acid. And for any weak acid, when in doubt, ice it out. So for any weak acid, we're always going to write out a dissociation for it. It'll dissociate into H+, and its conjugate base, ClO- hypochlorite. Then we're going to do a little ICE action. We're starting with 0.15 molar of this, and 0 and 0. It's going to be minus x plus x and plus x. 0 plus x is x, 0 plus x is x, and 0.15 minus x is 0.15 minus x. So now we're 1/2 of the way there. We have to write out our equilibrium expression, which is Ka is equal to products, which is H plus and ClO minus over reactants, the HClO. So now let's plug in our values. And remember that if our K is on order of 10 to the negative 5th or smaller, we can assume that this change is insignificant compared to our initial amount, unless the initial amount is 0, in which case it is significant. So compared to the 0.15, that change is insignificant. So we're going to plug everything in. 3 times 10 to the negative 8th is equal to x times x, which is x squared, divided by 0.15. So we'll multiply both sides by 0.15 and take the square root, and we'll end up getting 6.7 times 10 to the negative 5th. Now remember, that represents the H plus concentration. So if we take the negative log of that, we're getting the pH. So the pH, which is the negative log of the 6.7 times 10 to the negative 5th, is equal to 4.17. And then to finish this problem off, we just need to remember that pH plus pOH equals 14, specifically at 25 degrees Celsius. So we'll take this value and we'll subtract it from 14, and we'll end up getting that the pOH, which is what we're solving for, is equal to 9.83, which, well, close enough, equal to E. So here we're trying to arrange these in order of increasing acid strength. So notice that these are all carboxylic acids. Carboxylic acids have the motif, the COOH. Remember, the way that we can make carboxylic acids more acidic is by adding in more electronegative atoms downstream of our functional group. So when we rank these, acetic acid is going to be the least because it only has hydrogens. After that, if we look at these, molecule 1 has 1 bromine. Okay, well, that's great, but what has more electronegativity than just 1 bromine? Well, 2 bromines. So 3 is going to be next. And what is stronger than that? Well, 1, 2, 3 chlorines. So this trichloroacetic acid is going to be the greatest of all. So it's 2, then 1, then 3, then 4. Choice B. In this problem, we find our protagonist, Rick T. Cat, experiencing hyperventilation, vomiting, dizziness, and a diffuse burning sensation. They find out that the relative concentration of carbonic acid, H2CO3, to bicarbonate, HCO3-, is 1.5 millimolar to 30 millimolar. So, what do we have here? We have a combination of a conjugate weak acid and a weak base pair together in appreciable concentrations. Hark! We have ourselves a buffer alert! Whenever we recognize that we have a buffer, we can use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of base over acid. It doesn't matter if we're looking at concentration or number of moles. Henderson-Hasselbalch is a robust equation, so as long as we just have the ratio of base to acid in whatever units, as long as we're consistent with our units, we'll be good to go. Okay, so we need to figure out which K value to use, and if we think about Ka1 versus Ka2, Ka1 is H2CO3 dissociating into H plus and bicarbonate HCO3-. Ka2 would be HCO3- dissociating into H plus and CO3-2-. So we need to use the one that involves our conjugate weak acid, weak base pair, which is Ka1. So when we solve here, we're going to use pH is equal to the negative log of Ka1, because again, that relates our conjugate weak acid, weak base pair that we have, which is 4.3 times 10 to the negative 7th. Plus the log of base, which is our bicarbonate, which is 30 millimoles per liter, over our acid, which is 1.5 millimoles per liter. And when it's all said and done, we'll end up getting that pH is equal to 7.67. So it turns out that Rick T. Cat is experiencing some sort of alkalosis, because blood pH should be about 7.4. And if it gets much higher or much lower than that, problems occur. Okay, here we're trying to figure out what happens when uranium-238 goes through 8 rounds of alpha decay and 5 rounds of beta decay. So first of all, uranium-238. So uranium is element number 92, so it has 92 protons. And 238 specifically would have 238 atomic mass units. Okay, so if it's going through 8 rounds of alpha decay, remember, each alpha particle consists of 2 protons and 2 neutrons for a total of 4 atomic mass units. And then it's also going through we're told 5 beta decays. Each beta decay has an overall mass of 0, in the grand scheme of things, and -1 as its atomic charge. And we're ending up with some sort of mystery isotope, which we're trying to find the identity of. So I'm going to call it M for mystery. Okay. So I always like to start by figuring out the elemental identity of our mystery isotope. And what we're going to do is we're going to set each side of the reaction. So there's 92 protons in uranium. We're going to set that equal to, and we're going to find the total atomic number of all of these particles and solve for X first. So 92 is equal to 8 times 2, that's from the alpha decays, plus 5 times -1, that's from the beta decays, plus X. So 92 is equal to 16 plus -5 plus X, which means 92 is equal to 11 plus X, which means that X is equal to 81. So that means that we must be looking at none other than thallium. So this is TL. So we're getting pretty close to figuring out the identity of our mystery isotope. We're looking at something that has 81 protons. Now then, to figure out what the mass number is, we're going to do the same thing, only with these numbers up here. So we have 238 is equal to 8 times 4 plus 5 times 0 plus Y. So we'll subtract 8 times 4 is 32. We'll subtract that from both sides and get 206, and that's going to be equal to Y, which means that we're looking at thallium 206. And that's our answer. All right, let's make a rate law based on a mechanism. Whenever you base a rate law on a mechanism, remember, we always want to hone in on the slow step. That is the most important step for determining how fast a reaction can go. So we can write a rate law based off of this. It's going to be rate is equal to some constant K times, and then we have N2O2 times H2. Okay, great. Now, is this a good rate law? And the answer is, well, appropriately enough, no. No, it is not. Why not? Because there's N2O2 in it. N2O2 is an intermediate. Any self-respecting rate law cannot have an intermediate in it. So what we need to do is use a little bit of chemistry to help solve for our intermediate in terms of reactants or catalysts. So what I mean by that is, while the slow step is slowly going and taking its good old time, the fast step has a chance to reach equilibrium. And at equilibrium, the forward rate, so I'm going to call this KF for the forward rate. So the forward rate would be NO squared based off of this. It's going to be equal to the reverse rate, which would be KR and then N2O2. So our goal is to solve for N2O2 so we can mathematically replace it in the equation. So to do that, we're going to divide both sides by K sub R, and any number divided by itself is 1, and a constant divided by a constant is just a whole new constant. We don't care what it is. So I'm just going to call this whole new constant, let's call it K pi, because it's arbitrary. We don't care. We love it. And pi is fun, so we'll call it that. So now what we're going to do is we're going to take this and we're going to substitute it in in place of the N2O2. So what we'll end up getting is that our rate is equal to a constant times a constant. Again, it's just a whole new constant. We sometimes call this K observed, or OBS for observed. We have the NO squared. And our H2, in the meanwhile, nothing's happened to the H2, so it's still just H2. And now we get this, a good working rate law. So our answer is choice D.